Good evening and welcome to Chapter 16. This is 16.6. We're finding the hydronium ion concentration and pH of both strong and weak acid solutions. We've been doing quite a bit of work with strong acid solutions, so we're not going to spend a ton of time with that. We're going to actually skip some of those. So if we jump right in, it says finding the H3O concentration and pH of strong and weak acid solutions. We know that in most strong or weak acid solutions, the autoionization actually produces less H3O than pure water and can be ignored. Why is that? This is actually basically Le Chatelier's principle. So if we take a strong acid, just for example, HCl, we add it to water, and we're going to get H3O pluses and Cl minuses. If we look at what water does, the autoionization, this is a two-sided arrow, we're going to get H3O pluses as well as OH minuses. If you can see, we're adding H3O pluses, so the concentration of H3O pluses in this case is going to go up, right? Which is going to cause the equilibrium to shift back to the left. Le Chatelier's principle tells us that we're going to shift it that way, so we actually have a concentration of H3O going down in water, and so we don't actually have to worry about that. Okay, so we're jumping on to strong acids. Strong acids completely dissociate in solution, so all we have to do to find the pH or the hydronium ion concentration is to use one of these handy-dandy formulas. We don't actually have to do extra work with it. So we've got that formula, or we could go the reverse, where H3O plus is equal to 10 to the negative pH. Those formulas will be useful later, but we actually have to do some things before we get there. So weak acids, the pH of weak acids are higher than strong acids. Remember, the stronger an acid is, the lower the pH. And that's because they only partially ionize, which means we have to bring ice charts into play. So if we look here, we have an example. It says find the hydronium ion concentration of a 0.100 molar HCN solution, and our Ka is 4.9 times 10 to the negative 9th. If you're having trouble finding these Kas, there's an appendix in the back that has them, or this one was just stolen right from the problem. So our first step in any of these equilibrium problems is to write a balanced chemical equation. So we're going to take HCN, we're going to add water to it, and we're going to get H3O pluses and Cn minuses. So from here, we want to write our equilibrium constant expression, Ka, is equal to our products, which in this case, H3O plus and Cn minus, over our concentration of our HCN. Remember that we do not want to put water in there because water's concentration does not change. Okay, so let's make an ice chart. So we've got ICE. We've got our HCN initial concentration is 0.100. Water we are not concerned with. Our initial concentration of H3O and Cn is 0. Now finishing out our ice chart, minus X plus X plus X. We're going to go 0.100 minus X, and that's going to be X and X. So now we're ready to plug this in. So over here we've got 4.9 times 10 to the negative 10 is equal to X times X over 0.100 minus X. At this point, this is where we can lose this little X right there, which is going to leave us with X squared over 0.1 equals 4.9 times 10 to the negative 10th. So to find the answer to this, we're going to multiply 0.1 on each side. That gets it to go away on this side. And then, so we've got X squared equals 4.9 times 10 to the negative 10th times 0.1. And we're going to take the square root of both sides. And X should come out to be 7.0 times 10 to the negative 6th. And that is a molarity, and that is our question for that first one. So pretty simple. All we have to do is use an ice chart, plug it all in, and solve. On to the next one. This next one says find the pH of a 0.2 molar HNO2 solution. The Ka of said solution is going to be 4.6 times 10 to the negative 4th. Now I'm going to go ahead and go on record immediately and say that this one would not be valid with the assumption, but we're going to go ahead and solve it with the assumption. So if you're checking later, this does not fit up with the answer to the text. All right, so here we go. We've got our first step is to write a balanced equation. So we've got HNO2 plus H2O, arrow, arrow. We're going to get H3O plus, and we're going to get NO2 minuses. HNO2, our initial concentration is going to be 0.200. Make our ice chart here. Water we don't care about. 0 here, minus X, plus X, plus X. We're going to get 0.200 minus X. That's going to be X, and that's going to be X. So if we fill in our equilibrium constant expression, we're going to have Ka is equal to products over reactants. So again, we've got H3O plus times our concentration of NO2 minus over HNO2, nitrous acid. All right, so we're ready to plug it in and solve. At this point, we've got 4.6 times 10 to the negative fourth is equal to X times X over 0.200 minus X. Again, as I said at the beginning of this problem, we are not able to make this assumption and get the correct answer, but we're going to still go ahead and do it. So we've got X squared over 0.2 is equal to 4.6 times 10 to the negative fourth. And so to solve here, we're going to take 4.6 times 10 to the negative fourth. And we're going to multiply that by 0.2. And we're going to get X squared equals 0.00 or 9.2 times 10 to the negative fifth. And now we're going to take the square root of both sides. Square root of both sides. And that should give us X. We get a value, which is our hydronium ion concentration, is a value of 9.59 times 10 to the negative third. Now, unfortunately, we're not done. We are just at our hydronium ion concentration, so we have to take it a step further. So we're going to go from our hydronium ion concentration to our pH. pH is the negative log of our hydronium ion concentration. And so we're just going to take the negative log of 9.59 times 10 to the negative third. And this should give us our pH. And that should give us 2.02. And there we have it. That's actually the correct answer, but sometimes it won't be. So if we look at this next one here, continuing the same work, now we're just going to work backwards. We have a pH this time, and we're trying to find a Ka. So again, we're going to start with the reaction. So HA plus H2O gives us H3O pluses and A minuses. This is a generic reaction. You'll oftentimes see this for weak acids. We'll plug this in. Ka is equal to A minus times the hydronium ion concentration. I did it in a little different order, but it'll still work. Times the concentration of HA. So if we fill in our ice chart, ICE, we've got 0.100. Water, remember? 0, 0, minus X, plus X, plus X. We've got 0.100 minus X. We've got X, we've got X. So let's start plugging some stuff in. We are looking for the Ka. So at this point, we have a pH of 4.25. So if we take 10, if we go look at it this way, hydronium ion concentration equals 10 to the negative pH, that will give us our hydronium ion concentration, which will give us our X value. And we can do a lot of good work at this point. So, at this point, I want you to take a couple of minutes and solve this problem, and I'll be back.